Hi everyone, welcome back. This is actually take 4 of this video, so let's hope it works this time. The title of this section is 6.1 using fundamental identities, so it's part 2 from yesterday's video. The essential question is still the same: how can I use trig identities to simplify expressions? Alright, so we're going to go ahead and start off right away with example 1. So example 1, we're just going to simplify. And what we're simplifying is just basically a complicated trig function into something a little more simple. What I noticed in this one is that I have 3 separate trig functions all in one expression. And my goal is, again, to try to convert it to as little as possible. And in this case, I want one trig function. So I see a cosine, I see a sine, and I see tangent. I know tangent can be converted into sine x over cosine x. Alright, so by doing that, I'm going to go ahead and multiply the sine x into this, and this becomes cosine of x plus sine squared of x over cosine of x. Okay, so looking at that, I'm like, what do I do? So let's try adding them. First off, this has a denominator of 1. This has a denominator of cosine of x. So I'm actually going to need to multiply the first one by cosine of x. So multiplying just the first term by cosine of x over cosine of x. Leading down here, I'm going to get cosine squared of x over cosine x plus sine squared of x over cosine x. Now, if you had wondered, like, why would Mr. Doan make this more complicated by adding in that denominator, it's also because I wanted to see that, well, here I have a sine squared, and I know that sine squared plus cosine squared would get me 1. So it's actually pretty convenient here that multiplying the top and bottom by cosine of x will allow me to get there. Because now that I have a common denominator, I can combine the numerators with the common denominator, and this simplifies. Cosine squared of x plus sine squared of x, as our identity says, is 1, and then it's 1 over cosine of x, which just simplifies down to secant of x. And just like that, that's the end of that problem. Okay, so moving on then to example 2, where we start off right off the bat with a fraction. So we're going to say to rewrite expression so it's not a fraction. Alright, the expression I'm dealing with is 1 over 1 plus cosine of x. And looking here, this one's a little more difficult to work with because you kind of have to have an understanding of the trig identities. In this case, we're going to go ahead and go back to that same one from earlier, cosine squared of x plus sine squared of x equals 1. The reason I'm going back to this one is because there's a way to manipulate this so that I somehow get at least part of this. I'm going to subtract both sides by cosine squared of x, and I think some of you might see where this leads. Sine squared of x then is going to equal to 1 minus cosine squared of x. Here I have a difference of 2 squares. So yesterday you practiced some of the factoring involving trig functions. Here I'm going to go ahead and try that. I have 1 plus cosine of x times 1 minus cosine of x. This is exactly what I wanted because 1 plus cosine of x is already here. Which means if I somehow incorporate this into this expression, I'm going to be able to get this guy, this complicated little denominator, to become something more simple like sine squared of x. So just like I did earlier, I'm going to multiply this term by something to change its denominator, and I'm going to multiply it by 1 minus cosine of x. This becomes 1 minus cosine of x over 1 minus cosine squared of x. So now that I already shown here that 1 minus cosine squared of x is the equivalent of sine squared x, I'm going to rewrite this one more time. 1 minus cosine of x over sine squared x. At this point, it doesn't look like I can do much else, but I'm going to do something kind of like at the reverse of that one. I'm going to split this into two separate fractions. Okay, the first one is going to be 1 over sine squared x. The other is going to be minus cosine x over sine squared x. Here, I know that this can be changed because it is a reciprocal function to, or reciprocal identity, cosecant squared of x. The other one's going to be a little more tricky, and you do kind of have to think about it. Here I'd see sine squared x, which technically means there's two sine x's. Okay. One way we could do this is put cosine of x over sine x times 1 over sine x. Basically split up the sine x's, put cosine x on top of 1, and then the other one's got to be 1 because cosine x times 1 will give me that cosine of x again. And from here I can simplify these guys even further. So cosecant squared stays the same. This one becomes cotangent of x times cosecant x. Now, at this point, the only thing I could do is factor out cosecant of x. And unlike yesterday, it won't lead to anything simpler. So this is actually as simple as we get. So we tried, but that's as far as we're going to get. And at least it's better than dealing with a fraction. All right, so this right here will be our answer. All right, now we have one final example, example 3. And here we're going to be doing some trig substitution. Now the instructions for this one are going to be a little bit confusing. I'm going to write out the entire thing and try to explain each part of it. So it says to use the substitution x equals sine theta, with theta being between 0 and pi over 2, to express this expression, square root of 36 minus x squared, as a trig function. In other words, I want to change this guy, this whole radical 36 minus x squared, into a trig function using one of my 6 trig identities. And the way we're going to do that is by substituting in this x value. So the method of doing it is actually not too bad. It's pretty simple, but why we're doing it, I'll explain afterwards. So I'm going to plug this in for x. So I'm going to get square root of 36 minus 6 sine theta squared. And from there, I just simplify. So square root of 36 minus 36 sine squared theta. Here I see that they have a 36 in common, so let's go ahead and factor that out. 36 times 1 minus sine squared theta. By now, hopefully you recognize that this is one of our most popular trig identities, that this is going to convert into cosine squared theta. So we have the square root of 36 cosine squared theta. And because they are both perfect squares, we get to simplify this down to just 6 cosine theta. Alright, so that right there will be our answer. In other words, this whole thing as a trig function is 6 cosine theta. Now some of you might ask, wait, where the heck did that come from? First off, looking here, I can actually draw a triangle. So I have x equals 6 sine theta with this specification for where my triangle should be. So between 0 and pi over 2, I know that my triangle is going to be in quadrant 1. Alright, so here, x equals 6 sine theta, which means that sine theta was equal to x over 6. So x is my opposite, and 6 is my hypotenuse. Which means that third side, using the Pythagorean theorem, has to be 36 minus x squared. Alright, so kind of seeing things connect together now. This triangle is defined by that angle theta. So if I were to take cosine of that angle, cosine theta, I would get the adjacent root of 36 minus x squared all over 6. And now hopefully the pieces are coming together for you. If I were to multiply 6 to both sides to get that radical all by itself, what I've just proven to myself is that 6 cosine theta is equal to square root of 36 minus x squared, which I found by going through some substitution. All right. So in terms of working tomorrow, all you're going to have to do is this part. So you're not going to have to worry about proving the whole triangle, but that's just kind of some background information to make sure you understand why that's happening. All right. So go ahead, rewind and replay as needed. Otherwise, bring in your questions tomorrow and move on to the Google Forms. Have a good day, you guys.